The statement that one individual remains the first and only physicist to win 2 Nobel Prizes is not merely a record or a statistical curiosity. It is a reflection of an extraordinary convergence of intellect, perseverance, originality, and historical impact. In the entire history of modern science, countless physicists have transformed human understanding of nature, yet only Marie Curie crossed the threshold of earning 2 Nobel Prizes while being fundamentally rooted in physics. This achievement stands unmatched not because others lacked brilliance, but because the scope and depth of her contributions reshaped more than one scientific discipline at its core. The Nobel Prize itself was designed to recognize discoveries that confer the greatest benefit to humankind. Winning it once places a scientist among the most influential minds of their era. Winning it twice, especially in different scientific categories, elevates that individual beyond normal classification. Marie Curie achieved this rare honor through discoveries that were not incremental improvements, but revolutionary shifts in how matter, energy, and atoms were understood. Her work did not merely answer existing questions. It created entirely new ones and opened doors to fields that previously did not exist. In 1903, Marie Curie received the Nobel Prize in Physics for her pioneering research into radiation, a phenomenon that was mysterious and poorly understood at the time. This recognition alone would have secured her place in history. However, her scientific journey did not pause with acclaim. Instead, she continued her investigations with relentless focus, moving deeper into the atomic world. This continuation led to her second Nobel Prize in 1911, awarded in chemistry for the discovery of 2 new chemical elements and the isolation of radioactive substances. The fact that both awards stemmed from a single, evolving line of inquiry demonstrates the rare continuity and depth of her scientific vision. What makes her unique among physicists is not simply that she won 2 Nobel Prizes, but that both awards were earned independently and for original work. Many laureates build upon collaborative efforts or single discoveries. Marie Curie, however, was recognized twice for distinct breakthroughs that required different experimental methods, theoretical interpretations, and scientific frameworks. The first prize honored her contribution to understanding radiation as a physical phenomenon emerging from the atom. The second acknowledged her chemical mastery in isolating radioactive elements and determining their properties. In essence, she proved that the boundaries between scientific disciplines are human-made, while nature itself operates as a unified whole. Her achievement becomes even more remarkable when viewed against the scientific environment of the late 19th and early 20th centuries. Physics at the time was dominated by classical mechanics, and the atom was still considered indivisible by many. Marie Curie's work challenged these assumptions directly. By demonstrating that atoms could emit energy spontaneously, she undermined long-held beliefs and laid the groundwork for quantum physics and nuclear science. Her research forced physicists to reconsider the stability of matter itself, leading eventually to breakthroughs by later scientists such as Einstein, Bohr, and Heisenberg. Equally important is the historical context in which she worked. Marie Curie conducted her research during an era when women were systematically excluded from scientific institutions, denied academic positions, and often ignored in professional recognition. That she not only entered physics, but dominated it to such an extent that she won its highest honor twice, is almost without precedent. Her success was not supported by privilege or institutional backing. It was achieved through sheer determination, intellectual rigor, and personal sacrifice. This makes her status as the only physicist with 2 Nobel Prizes not just a scientific milestone, but a social one. Unlike some scientific figures whose reputations grew through influence and authority, Marie Curie's recognition came from empirical evidence. Her experiments were meticulous, exhausting, and dangerous. She worked with radioactive materials without understanding their long-term health effects, often carrying test tubes of radium in her pockets because she found their glow fascinating. The Nobel Committee did not award her prizes for theoretical speculation or philosophical insight alone, but for experimental results that could be measured, verified, and reproduced. This underscores the fact that her dual Nobel recognition was grounded in the most rigorous standards of science. Another reason her achievement remains unmatched is the sheer difficulty of producing Nobel-level discoveries more than once. Science is cumulative, and once a field advances, the threshold for groundbreaking work rises. Marie Curie overcame this by essentially inventing a new field and then mastering it completely. Radioactivity was not simply a topic she studied, it was a domain she defined. By the time others entered the field, she had already mapped its foundations. Winning a Nobel Prize in physics acknowledged her role in uncovering the phenomenon itself, while the Chemistry Prize recognized her command over its practical and elemental nature. It is also important to note that while other individuals have won 2 Nobel Prizes, none share her specific distinction as a physicist. Some have received Nobel Prizes in different categories, such as peace or chemistry, but Marie Curie's identity as a physicist remained central to her work. Her approach to chemistry was deeply physical, rooted in atomic structure and energy emission. Even when she isolated new elements, her motivation was to understand the physical forces governing matter. This reinforces the idea that her 2 Nobel Prizes were not separate achievements, but 2 chapters of the same scientific narrative. The enduring uniqueness of her accomplishment also reflects the evolving nature of science itself. Modern research is increasingly collaborative, involving large teams and complex instruments. While this has accelerated discovery, it has also made individual recognition rarer. Marie Curie worked in a time when solitary persistence could still yield monumental results. Her laboratory was modest, her resources limited, yet her conclusions reshaped scientific understanding worldwide. In today's environment, replicating such an individual trajectory would be extraordinarily difficult, which further explains why her record remains intact. Beyond numbers and titles, the significance of being the only physicist to win 2 Nobel Prizes lies in what it represents about human potential. Marie Curie's life demonstrates that scientific excellence is not confined by gender, nationality, or social status. She began her career as a poor student from a politically oppressed country and ended it as one of the most influential scientists in history. Her dual Nobel recognition symbolizes the triumph of curiosity and perseverance over limitation and prejudice. Her achievement also had a profound impact on how society perceives science. By winning 2 Nobel Prizes, she became a global symbol of intellectual authority at a time when science was rapidly reshaping the modern world. Governments, universities, and medical institutions sought her expertise. Her work influenced cancer treatment, energy research, and atomic theory, extending far beyond academic physics. This broad influence reinforces why her recognition was not excessive but necessary. The scope of her impact demanded it. Even today, over a century later, no physicist has replicated her feat. This is not due to a lack of talent in modern science, but because Marie Curie's discoveries occurred at a unique historical moment when foundational questions about matter were still unanswered. She stood at the threshold between classical and modern physics, and she crossed it decisively. Her 2 Nobel Prizes mark that transition and serve as milestones in humanity's quest to understand the universe. Ultimately, the fact that Marie Curie remains the only physicist to win 2 Nobel Prizes is a testament to the rarity of true scientific revolution. It reminds us that transformative discoveries do not happen often, and when they do, they require extraordinary minds willing to challenge convention, endure hardship, and pursue truth at any cost. Her legacy is not confined to awards or records. It lives on in every scientific exploration of the atom, every medical use of radiation, and every researcher inspired by her example. To fully grasp why this achievement has never been repeated, it is essential to understand how Marie Curie's work fundamentally altered the meaning of scientific excellence. Her 2 Nobel Prizes were not the result of chance, timing, or institutional support, but the outcome of sustained intellectual courage. She pursued questions that others either ignored or believed were already answered. In doing so, she redefined what it meant to be a physicist at a moment when physics itself was undergoing its most dramatic transformation. At the time of her discoveries, science was not divided into rigid disciplines as it is today. Marie Curie moved fluidly between physics and chemistry because the atomic world demanded such an approach. Her recognition by the Nobel Committee in 2 different categories reflects not a shift in her identity, but the expanding reach of her discoveries. She did not abandon physics to pursue chemistry. Rather, her physical insights compelled her to engage with chemical methods. This seamless integration of disciplines is one reason her accomplishments remain so difficult to replicate. The rarity of her distinction also lies in the level of originality required to earn 2 Nobel Prizes independently. Many scientists make a single breakthrough and spend the rest of their careers refining or extending it. Marie Curie did something far more demanding. She uncovered a phenomenon unknown to science and then mastered its practical, theoretical, and material dimensions. The first Nobel Prize recognized the discovery of radioactivity as a fundamental physical process. The second honored the isolation, measurement, and characterization of new elements that embodied that process. Each achievement required a different kind of genius, yet both emerged from the same relentless pursuit of truth. Her work forced scientists to confront uncomfortable implications about the nature of matter. If atoms could emit energy spontaneously, then classical physics was incomplete. This realization destabilized long-standing assumptions and compelled physicists to rethink the structure of reality itself. Marie Curie did not merely contribute to this shift, she was one of its primary catalysts. That level of influence is exceedingly rare, even among Nobel laureates, and helps explain why her achievements stand alone. Another crucial factor is the personal cost at which her discoveries were made. Marie Curie worked in conditions that would now be considered unacceptable. She processed tons of pitchblende by hand, often in a poorly ventilated shed, exposing herself to radiation daily. At the time, the dangers were unknown, but the physical toll on her body was real and lasting. Her health deteriorated gradually, yet she never slowed her work. This willingness to endure hardship in pursuit of knowledge adds a dimension of sacrifice that deepens the significance of her recognition. Her 2 Nobel Prizes also highlight the difference between achievement and ambition. Marie Curie did not set out to win awards or break records. In fact, she was famously uncomfortable with fame and public attention. When offered opportunities to profit from her discoveries, she refused, insisting that scientific knowledge belonged to humanity. This ethical stance distinguished her from many contemporaries and reinforced the moral authority of her work. The Nobel Committee recognized not only her discoveries, but the integrity with which they were pursued. The persistence of her unique status also reflects structural changes in science over the past century. Today, groundbreaking research often emerges from large teams working across institutions and countries. While this collaboration has led to remarkable advances, it has also made individual recognition more complex. Marie Curie operated in an era when a single mind, armed with determination and insight, could still reshape entire fields. Her career represents a moment in scientific history that may never fully return. Yet even within her own time, her accomplishments were extraordinary. Many physicists worked alongside her, but none matched the breadth or depth of her impact. Her discoveries influenced not only theoretical physics, but also medicine, industry, and public policy. The medical use of radiation, particularly in cancer treatment, traces directly back to her work. This practical application of fundamental physics further distinguishes her achievements from those of scientists whose contributions remained confined to theory. It is also worth noting that her dual Nobel recognition challenged societal expectations in ways that extended far beyond science. As a woman in a male-dominated field, her success disrupted entrenched beliefs about intellectual capability and authority. Each Nobel Prize served as a public affirmation that excellence knows no gender. This broader cultural impact amplifies the importance of her achievement and helps explain why it continues to resonate more than a century later. Her legacy is further strengthened by the fact that her influence extended across generations. Scientists who built the foundations of quantum mechanics and nuclear physics were directly inspired by her discoveries. Even those who disagreed with her interpretations were forced to engage with her evidence. In science, this is the highest form of recognition, to shape the questions that others must answer. Winning 2 Nobel Prizes reflects not only what she discovered, but how deeply those discoveries penetrated the scientific imagination. The continued absence of another physicist with 2 Nobel Prizes also speaks to the evolving criteria of scientific recognition. As knowledge expands, revolutionary discoveries become rarer. Modern physics explores realms that require enormous resources and collective effort. While individual brilliance remains essential, the kind of solitary, foundational work that defined Marie Curie's career has become increasingly uncommon. Her achievement thus stands as both a record and a historical marker. Beyond institutional recognition, her story endures because it embodies the ideals of science itself. Curiosity, honesty, perseverance, and humility guided her work. She did not seek to dominate her field or claim ownership over knowledge. Instead, she sought understanding and shared it freely. This spirit of inquiry is what ultimately earned her 2 Nobel Prizes and secured her place as a singular figure in the history of physics. Even today, when science has advanced far beyond what Marie Curie could have imagined, her contributions remain relevant. The study of atomic energy, radiation, and subatomic particles continues to build upon principles she helped establish. Every modern exploration of nuclear processes carries echoes of her original insights. This enduring relevance underscores why her dual recognition was not an anomaly, but a reflection of lasting significance. Her distinction as the only physicist to win 2 Nobel Prizes is therefore not a mere historical footnote. It is a testament to the power of sustained curiosity and fearless exploration. It reminds us that true breakthroughs often arise from questioning the most basic assumptions and refusing to accept easy answers. Marie Curie's life and work exemplify this principle with unmatched clarity. In the end, her achievement challenges how we measure success in science. Awards and titles matter, but they are secondary to impact. Marie Curie's 2 Nobel Prizes symbolize a lifetime of contributions that reshaped human understanding of nature. They mark the rare moments when discovery transcends discipline and alters the trajectory of knowledge itself. This is why, more than a century later, her record remains unbroken. It is not simply because no one has matched her brilliance, but because few have had the opportunity, courage, and perseverance to redefine science at such a fundamental level. Her legacy stands as a reminder that the greatest achievements are born not from the pursuit of recognition, but from an unwavering commitment to truth. To say that Marie Curie changed physics and chemistry forever is not an exaggeration or a tribute shaped by admiration. It is a precise description of how deeply her work altered the structure, direction, and language of modern science. Before her discoveries, physics and chemistry were largely separate domains with clearly defined boundaries. After her work, those boundaries blurred, merged, and in some cases disappeared altogether. She did not simply add new knowledge to existing fields. She transformed the way scientists understood matter, energy, and the atom itself. At the end of the 19th century, physics was dominated by classical theories that treated atoms as stable, indivisible units. Chemistry focused on reactions between elements whose internal structures were considered irrelevant. Matter was assumed to be predictable, orderly, and fundamentally inert, unless acted upon by external forces. Into this stable and confident scientific world, you entered Marie Curie's research, which revealed that matter itself could be active, unstable, and capable of emitting energy spontaneously. This single realization shook the foundations of both disciplines. Her identification and naming of radioactivity introduced a phenomenon that could not be explained by classical physics or traditional chemistry. Radiation did not behave like heat, light, or electricity. It emerged from the atom without any visible cause, persisted over time, and was unaffected by temperature, pressure, or chemical reactions. This forced physicists to confront the possibility that atoms were not solid and unchanging, but complex systems with internal processes. Chemistry, too, was compelled to evolve, because elements were no longer defined solely by their chemical behavior, but by their atomic properties. Marie Curie's work effectively shifted scientific attention from molecules to atoms, and from atoms to their internal structure. This shift marked the beginning of modern atomic science. By demonstrating that radioactivity was an atomic property, she provided the first clear evidence that atoms could transform, decay, and release energy. This discovery directly contradicted long-standing beliefs and required a rethinking of the most basic assumptions about matter. Physics could no longer ignore the atom's interior, and chemistry could no longer treat atoms as immutable building blocks. The discovery of new elements such as polonium and radium further expanded the scope of both sciences. These elements did not fit neatly into existing chemical classifications because their defining feature was not reactivity, but radioactivity. Their behavior could not be fully understood through chemical equations alone. It required an understanding of nuclear processes. In isolating and studying these elements, Marie Curie introduced techniques and concepts that permanently altered chemical analysis and experimentation. Her work also changed the methodology of science. She combined precise measurement, physical theory, and chemical separation in ways that were unprecedented. This interdisciplinary approach became a model for future research, particularly in fields that operate at the boundaries of traditional disciplines. The emergence of nuclear physics, radiochemistry, and later particle physics can all be traced back to this methodological transformation. Science became less about fitting observations into existing frameworks and more about building new frameworks when evidence demanded it. The impact on physics was especially profound. Radioactivity revealed that energy could be stored within matter itself, an idea that later found theoretical expression in Einstein's equation relating mass and energy. While Marie Curie did not develop this equation, her experimental evidence made such a relationship conceivable. Without the demonstration that atoms could release enormous amounts of energy, the concept of mass-energy equivalence might have remained purely speculative. In this way, her work prepared the ground for some of the most important theoretical advances of the 20th century. Chemistry, too, was transformed at a fundamental level. The discovery of radioactive elements challenged the periodic table and forced chemists to reconsider how elements were classified. Atomic weight, once considered a fixed property, became less certain as radioactive decay revealed that elements could change into other elements over time. This phenomenon, once thought impossible, introduced a dynamic view of chemical identity. Elements were no longer eternal. They had lifetimes, transformations, and histories. Marie Curie's influence extended beyond theory into practical application, further cementing her role as a transformative figure. The medical use of radiation, particularly in diagnosing and treating disease, emerged directly from her research. This application required a deep understanding of both physical radiation and chemical substances, reinforcing the inseparable nature of the two sciences in the modern era. Physics provided the principles, chemistry provided the materials, and together they changed medicine forever. Her discoveries also altered how scientists thought about time and scale. Radioactive decay introduced processes that operated over vast timescales, from fractions of a second to millions of years. This had implications not only for physics and chemistry, but also for geology, archaeology, and cosmology. Techniques such as radiometric dating, which rely on principles of radioactivity, transformed humanity's understanding of Earth's age and history. These advances stem directly from the scientific revolution she initiated. Another lasting change was in the philosophy of science itself. Marie Curie's work demonstrated that nature could behave in ways that defied intuition and classical logic. This encouraged scientists to embrace uncertainty, probability, and abstract models. The deterministic universe of classical physics gave way to a more complex and nuanced view, paving the way for quantum mechanics. While she was not a quantum theorist, her discoveries created the experimental conditions that made quantum theory necessary. Her influence also reshaped scientific education and research institutions. Laboratories began to incorporate new instruments, safety protocols, and research goals centered on atomic and nuclear phenomena. Entire departments and institutes were founded to study radioactivity and its applications. The very structure of scientific research changed, reflecting the new priorities and possibilities her work revealed. It is important to recognize that this transformation was not immediate or universally welcomed. Many scientists resisted the implications of radioactivity, viewing it as an anomaly rather than a fundamental phenomenon. Marie Curie persisted despite skepticism, refining her experiments and strengthening her evidence. Over time, the weight of her results became impossible to ignore. The eventual acceptance of her findings marked a turning point in both physics and chemistry, one from which there was no return. Her work also changed the language of science. Terms such as radioactivity, radioactive decay, and half-life became essential concepts, shaping how scientists describe natural processes. These concepts introduced a probabilistic and dynamic vocabulary that replaced older, static descriptions of matter. This linguistic shift reflects a deeper conceptual transformation that continues to influence scientific thought today. Perhaps the most enduring aspect of her impact is that it altered the direction of future research. After Marie Curie, the atom became the central focus of physical science. Questions about nuclear forces, particle interactions, and energy generation all trace their origins to her discoveries. Chemistry, meanwhile, expanded to include nuclear reactions and isotopic analysis, extending its reach far beyond traditional reactions between molecules. The fact that these changes remain central to modern science is proof that her influence was not temporary or limited. Physics and chemistry did not simply absorb her discoveries and move on. They reorganized themselves around them. This level of transformation is rare in the history of science and is reserved for those whose work redefines what is possible to know. In this sense, Marie Curie did not merely contribute to physics and chemistry. She reshaped their identities. She revealed that the most fundamental aspects of nature are hidden beneath the surface, waiting to be uncovered by those willing to challenge convention and endure uncertainty. Her discoveries marked the beginning of a new scientific era, one in which the atom became the gateway to understanding the universe. The permanence of Marie Curie's influence on physics and chemistry becomes even clearer when we examine how her discoveries reshaped the goals of scientific inquiry itself. Before her work, scientists largely sought to describe how matter behaved under external forces. After her discoveries, the focus shifted inward, toward understanding what matter is and how it can change from within. This shift fundamentally altered the questions scientists asked and the methods they used to answer them. One of the most revolutionary consequences of her work was the realization that energy was not only something transferred between objects, but something embedded deep inside matter. Radioactivity revealed that atoms contained enormous internal energy, released through natural processes without any external trigger. This insight shattered the classical separation between matter and energy and set the stage for a new physics in which these concepts were deeply connected. Chemistry, too, was forced to acknowledge that chemical behavior could not be fully understood without reference to atomic structure and internal forces. Her discoveries also transformed the concept of stability in science. Previously, stability was assumed to be a natural state of matter. Radioactive elements challenged this assumption by showing that instability could be fundamental and persistent. Some atoms naturally change over time, emitting particles and energy as part of their existence. This introduced a dynamic view of matter that replaced centuries of static thinking. Physics and chemistry both had to incorporate change, decay, and transformation as basic principles rather than exceptions. The idea that one element could transform into another had once belonged to the realm of ancient speculation. Marie Curie's work provided the first scientific evidence that such transformations were real, measurable, and governed by natural laws. This discovery redefined chemical identity. Elements were no longer eternal substances. They were stages in a process. This insight had profound implications, not only for chemistry, but for the understanding of the universe itself, including the origins of elements in stars and the evolution of matter over cosmic time. Her influence extended deeply into experimental science. The tools and techniques developed to study radioactivity became standard instruments in laboratories around the world. Precision measurement, long-term observation, and careful control of experimental conditions became essential practices. These methods strengthened the rigor of both physics and chemistry and set new standards for scientific reliability. Future discoveries in atomic and nuclear science relied heavily on these techniques. The transformation of chemistry was particularly striking. Traditional chemistry focused on reactions between substances, often without concern for what occurred inside atoms. After Marie Curie, chemists began to study isotopes, nuclear reactions, and atomic decay. This expansion gave rise to entirely new branches of chemistry, including radiochemistry and nuclear chemistry. These fields did not replace traditional chemistry, but extended it, making the discipline more comprehensive and powerful. Physics underwent an equally dramatic transformation. The discovery of radioactivity exposed the limitations of classical mechanics and electromagnetism. These theories could not explain why atoms emitted radiation spontaneously or why the emission followed statistical patterns rather than deterministic rules. This failure pushed physicists toward new theoretical frameworks. While Marie Curie herself remained primarily an experimental scientist, her findings demanded theoretical explanations that eventually led to quantum theory and nuclear physics. Her work also reshaped scientific collaboration. As the implications of radioactivity became clear, physicists and chemists were forced to work together more closely. Problems could no longer be solved within isolated disciplines. This collaborative approach became a defining feature of modern science. Large research institutes, interdisciplinary teams, and shared experimental facilities all trace part of their origin to the challenges her discoveries introduced. Beyond laboratories and theories, the impact of her work changed how science interacted with society. The application of radiation in medicine, industry, and research transformed everyday life. Medical imaging and cancer treatment emerged from principles she helped uncover. These applications reinforced the idea that fundamental science could lead to practical benefits, strengthening public support for scientific research and education. Her influence also altered ethical discussions within science. The power released from atomic processes raised questions about responsibility, safety, and the social consequences of discovery. While these debates intensified later, their roots lie in the recognition that understanding the atom carried immense potential. Marie Curie herself embodied a strong ethical stance, emphasizing openness and public benefit. This moral dimension became an integral part of how science was practiced and discussed. The educational impact of her work cannot be overstated. Physics and chemistry curricula around the world were rewritten to include atomic structure, radioactivity, and nuclear processes. Students no longer learned science as a closed system of fixed laws, but as an evolving exploration of hidden layers of reality. This educational shift inspired generations of scientists and broadened access to advanced scientific understanding. Her discoveries also influenced how time was understood in science. Radioactive decay introduced precise natural clocks that could measure time over vast scales. This allowed scientists to determine the age of rocks, planets, and even the Earth itself. Such insights connected physics and chemistry to geology, astronomy, and biology, reinforcing the unity of scientific knowledge. Once again, her work dissolved boundaries that had previously separated disciplines. The cultural impact of these changes further demonstrates how deeply she altered science. The atom became a symbol of modernity, power, and mystery. Public imagination was captivated by the idea that invisible forces governed the material world. This shift in perception influenced art, philosophy, and literature, showing that her scientific contributions resonated far beyond academic circles. Importantly, these transformations were not temporary phases. The atomic perspective introduced by Marie Curie remains central to science today. Modern research into energy generation, materials science, particle physics, and medical technology all rely on principles that emerged from her discoveries. This enduring relevance confirms that her impact was foundational rather than transitional. Her role in changing physics and chemistry forever is also evident in how scientific success is now defined. Breakthroughs are measured not only by immediate results, but by their capacity to open new fields and inspire future research. By this standard, her work stands among the most influential in history. It did not close questions, it multiplied them, ensuring decades of discovery to come. Even the way scientists think about uncertainty and probability can be traced back to the challenges her work posed. Radioactive decay follows statistical laws, not predictable paths. This forced physicists to accept that nature at its deepest level might be governed by probability rather than certainty. This acceptance became a cornerstone of modern physics and changed how scientific explanations are constructed. Her influence also reshaped the relationship between theory and experiment. Marie Curie's discoveries came from careful observation rather than abstract prediction. Yet those observations demanded new theories to explain them. This dynamic interaction between experiment and theory became a defining feature of 20th century science, accelerating progress across multiple fields. Ultimately, the reason her work changed physics and chemistry forever lies in its scope and depth. She revealed that the most fundamental aspects of reality were hidden within the atom, waiting to be explored. By opening that door, she redirected the course of scientific inquiry toward the smallest scales and the most powerful forces in nature. This transformation continues to shape how humanity understands the universe. From the structure of matter to the origin of energy, from medical technology to cosmic evolution, the legacy of her discoveries remains embedded in modern knowledge. Physics and chemistry are no longer what they were before her, and they can never return to that earlier state. The discovery of entirely new elements stands as one of the most concrete and lasting achievements in the history of science, and Marie Curie's role in this achievement represents a turning point in how humanity understands matter itself. Before her work, elements were thought to be rare, stable substances that had largely already been identified and classified. The periodic table was seen as nearing completion, and few scientists believed that truly new elements of fundamental importance were still waiting to be found. Marie Curie shattered this assumption through persistence, originality, and an unprecedented approach to studying matter. Her journey toward discovering new elements began with the investigation of mysterious radiation emitted by uranium. While other scientists observed this phenomenon, Marie Curie went further by carefully measuring the intensity of the radiation and comparing it across different materials. She noticed something extraordinary. Certain urania, rich minerals, emitted far more radiation than pure uranium itself. This observation led her to a bold conclusion. that these minerals must contain unknown substances far more radioactive than uranium. This idea was revolutionary because it suggested the existence of elements that science had never identified. Pursuing this insight required enormous effort and patience. Marie Curie worked with tons of pitchblende, a dense and complex mineral, breaking it down chemically step by step. The task was physically exhausting and mentally demanding. There were no shortcuts, no advanced machines, and no established methods for isolating substances that existed in minute quantities. She relied on careful chemical separation and precise physical measurement, repeating procedures countless times to ensure accuracy. This combination of chemistry and physics was essential to uncovering what lay hidden within the mineral. Through this relentless process, she identified the first new element, which she named polonium in honor of her homeland. Polonium was not just another chemical substance. It was proof that radioactivity could signal the presence of entirely new forms of matter. Its existence confirmed her hypothesis that radiation could be used as a tool to discover unknown elements. This marked a new method of scientific discovery, where invisible properties revealed what traditional chemical analysis could not. Her second discovery, radium, was even more significant. Radium emitted radiation far more intensely than any known substance, and isolating it required years of labor. From tons of pitchblende, Marie Curie extracted only tiny amounts of pure radium, demonstrating an extraordinary level of precision and determination. This achievement was remarkable not only because radium was new, but because it could be studied, measured, and characterized in detail. She determined its atomic weight, chemical behavior, and physical properties, firmly establishing it as a distinct element. The discovery of radium had immediate and far-reaching consequences. Its intense radiation challenged existing theories of atomic structure and energy. It showed that atoms were not passive building blocks of matter, but dynamic systems capable of releasing enormous amounts of energy. This realization reshaped both physics and chemistry, pushing scientists to explore the internal structure of the atom and laying the groundwork for nuclear science. Without the discovery of radium, many later developments in atomic theory might have been delayed by decades. What makes these discoveries especially significant is the method behind them. Marie Curie did not stumble upon new elements by chance. She developed a systematic approach that treated radioactivity as a measurable signal of unknown matter. This approach transformed the search for elements from a purely chemical process into a physical one. It expanded the concept of what an element could be and how it could be identified, influencing how scientists approached discovery in the future. Her work also redefined the meaning of chemical identity. Before polonium and radium, elements were classified mainly by how they reacted with other substances. Marie Curie showed that an element's atomic behavior, its radiation, stability, and decay was equally important. This insight led to the modern understanding of isotopes and nuclear properties, further deepening the connection between chemistry and physics. The discovery of new elements was not only a scientific triumph, but also a demonstration of intellectual courage. Marie Curie faced skepticism from the scientific community, which was hesitant to accept claims of unknown elements based on invisible radiation. Yet her evidence was precise, reproducible, and undeniable. Over time, her discoveries were confirmed and celebrated, proving that careful experimentation could reveal aspects of nature far beyond direct observation. The impact of discovering polonium and radium extended well beyond the laboratory. These elements became essential tools in medicine, research, and industry. Radium, in particular, played a key role in early cancer treatments and medical imaging, showing how fundamental discoveries could lead to life-saving applications. This practical impact reinforced the value of basic scientific research and strengthened public trust in science. Perhaps most importantly, her discovery of entirely new elements changed how scientists viewed the completeness of knowledge. It demonstrated that even well-established systems, like the periodic table, could still hold surprises. This realization encouraged a more open and exploratory attitude toward science, one that accepts uncertainty and welcomes the unknown. In the broader history of science, the discovery of new elements by Marie Curie stands as a symbol of discovery driven by curiosity rather than convenience. She worked without concern for personal profit, refusing to patent her methods and sharing her findings freely. Her goal was understanding, not ownership. This ethical approach amplified the significance of her discoveries and ensured their benefit to humanity. Working without fame, wealth, or privilege defines one of the most powerful aspects of Marie Curie's life and scientific legacy. In an era when scientific success was often supported by social status, institutional backing, and financial security, she stood as a rare example of someone who achieved extraordinary breakthroughs through determination alone. Her life shows that true scientific progress does not depend on comfort or recognition, but on commitment, discipline, and an unyielding desire to understand the truth. Marie Curie was born into a family that valued education but lacked wealth. Her early life was marked by political oppression and economic hardship. Opportunities for advanced study were limited, especially for women, and she faced restrictions that would have ended many ambitions before they began. Rather than accepting these limitations, she pursued knowledge with quiet resolve. She supported herself through teaching and personal sacrifice, saving every possible resource to continue her education. This early struggle shaped her character and instilled in her a deep respect for hard work and perseverance. When she arrived in Paris to study science, her circumstances did not improve immediately. She lived in small, poorly heated rooms, often skipping meals to afford books and tuition. Despite these hardships, she excelled academically, not because of special treatment or advantage, but because of her focus and discipline. Her achievements came from effort rather than opportunity, making her later success all the more remarkable. As her research progressed, she continued to work under conditions that reflected a lack of privilege. Her laboratory was a converted shed with minimal equipment and poor ventilation. It was far from the well-funded research facilities enjoyed by many of her contemporaries. Yet this environment did not stop her from producing world-changing discoveries. She relied on creativity, patience, and careful measurement instead of advanced tools. This ability to extract profound insights from limited resources highlights the depth of her scientific skill. Fame came to Marie Curie reluctantly and often against her will. She did not seek public attention, and she avoided social circles that revolved around status or prestige. When recognition arrived, she accepted it quietly and returned to her work. Even after winning the Nobel Prize, she continued to live simply, focusing on research rather than celebration. She viewed fame as a distraction from the pursuit of knowledge, not as a reward worth chasing. Her relationship with wealth further illustrates her principles. The discoveries she made, particularly those involving radium, had enormous commercial potential. She could have patented her methods and secured financial comfort for herself and her family. Instead, she chose to keep her work open and accessible, believing that scientific knowledge belonged to humanity as a whole. This decision reflected a profound ethical commitment and a willingness to sacrifice personal gain for the greater good. This refusal of wealth was not symbolic. It had real consequences. She struggled financially even as her work gained international importance. Funding for her research was often uncertain, and she depended on grants and donations to continue her experiments. Yet she never expressed regret over her choices. Her focus remained fixed on discovery, not material reward. This stance set her apart in a world where scientific success increasingly intersected with economic interest. Privilege also played no role in her ascent. She was not born into elite academic circles, nor did she benefit from powerful sponsors early in her career. As a woman and an immigrant, she faced skepticism and exclusion from institutions that favored tradition over talent. Despite these barriers, her work earned recognition through merit alone. And Marjolt's, challenging assumptions about who belongs in the Gauls, this scientific community. Even when she achieved global recognition, her lifestyle remained modest. She dressed simply, lived without luxury, and devoted her energy to teaching and research. Her priorities never shifted toward comfort or status. This consistency reveals a rare integrity, showing that her values were not shaped by circumstance, but by conviction. She believed that science was a responsibility, not a pathway to personal advancement. Her approach also influenced how others perceived science. By working without privilege or personal gain, she embodied the ideal of the scientist as a seeker of truth rather than a competitor for rewards. This image inspired trust and respect, reinforcing the idea that scientific progress should serve humanity rather than individual ambition. Her example encouraged future generations to pursue science for its intrinsic value. The absence of privilege in her life also shaped her resilience. She learned to persist without reassurance or external validation. Failures did not discourage her because she had already overcome so much simply to be present in the scientific world. This resilience allowed her to endure long years of experimentation, uncertainty, and physical strain. It also enabled her to maintain focus in the face of criticism and doubt. Perhaps the most powerful aspect of her working without fame, wealth, or privilege is the contrast between what she gave and what she received. She gave knowledge that transformed science, tools that advanced medicine, and an example of ethical integrity. In return, she accepted little more than the opportunity to continue her work. This imbalance underscores the selflessness at the heart of her legacy. In reflecting on this aspect of her life, it becomes clear that her achievements were not accidental. They were the result of a deliberate choice to value truth over recognition and purpose over profit. She demonstrated that the greatest discoveries often come from those who are willing to work in obscurity, guided by curiosity rather than reward. Ultimately, working without fame, wealth, or privilege was not a limitation for Marie Curie. It was a source of strength. It freed her from distractions and allowed her to devote herself fully to discovery. Her life stands as a reminder that the most enduring contributions to human knowledge are often made by those who seek understanding, not applause. Facing discrimination, yet never stopping, defines one of the most inspiring and enduring aspects of Marie Curie's life and legacy. Her scientific achievements are remarkable on their own, but when viewed alongside the barriers she faced because of her gender, nationality, and social position, they take on even greater meaning. Her story demonstrates that persistence in the face of exclusion can reshape not only individual destiny, but the direction of human knowledge itself. From the beginning of her life, discrimination shaped the opportunities available to Marie Curie. Growing up in a society where women were denied equal access to education, she encountered restrictions that were both formal and informal. Institutions that trained scientists were often closed to women, and those that allowed them rarely offered equal recognition or support. Rather than accepting these limits, she pursued education wherever it was possible, even when it required sacrifice, secrecy, and endurance. As a young student, she was excluded from many academic opportunities simply because of her gender. This exclusion forced her to study under difficult conditions, often without access to proper facilities or mentorship. Yet these obstacles did not weaken her resolve. Instead, they sharpened her independence and self-discipline. She learned to rely on her own abilities rather than institutional approval, a mindset that later allowed her to continue working even when recognition was denied. Discrimination followed her into professional life. As an immigrant in a foreign country, she was often viewed as an outsider. Her accent, background, and lack of social connections set her apart in academic circles dominated by tradition and hierarchy. Despite producing groundbreaking research, she was sometimes overlooked or undervalued in favor of colleagues who fit the established image of a scientist. These experiences revealed how deeply bias was embedded in scientific culture at the time. One of the most striking examples of discrimination came when her contributions were initially minimized or attributed to others. In collaborative environments, credit often flowed toward those with greater status or visibility. Marie Curie had to fight not through confrontation, but through evidence. She continued to produce results so compelling that they could not be ignored. Her response to discrimination was not protest, but persistence. Even after achieving international recognition, bias did not disappear. She was subjected to public scrutiny that went far beyond her scientific work. Her personal life was often judged more harshly than her male peers, and her character was questioned in ways that had nothing to do with her research. These attacks reflected broader societal expectations placed on women, especially those who stepped outside traditional roles. Yet she refused to let such judgment derail her work. Institutional discrimination also affected her career. Despite her accomplishments, she was denied positions and honors that were readily available to men with far fewer achievements. Decisions were often influenced by prejudice rather than merit. Still, she continued to teach, research, and mentor students, building scientific communities even when institutions failed to fully support her. What makes her perseverance especially powerful is that she did not allow discrimination to define her identity. She did not internalize rejection or doubt her abilities. Instead, she treated obstacles as conditions to work around rather than reasons to stop. This quiet resilience enabled her to maintain focus during long periods of isolation and uncertainty. Her refusal to stop also extended to moments of personal loss and hardship. When faced with emotional and professional challenges, she returned to her laboratory, finding purpose in discovery. Science became both her refuge and her contribution, allowing her to move forward despite adversity. This ability to continue, even when support was lacking, highlights the depth of her commitment. Her persistence gradually forced change. As her work gained recognition, it became impossible to deny her contributions. Each discovery weakened the barriers that sought to limit her. Over time, her presence itself challenged the norms of the scientific world, expanding the definition of who could be a scientist. While discrimination did not vanish, it lost its power to stop her. The broader impact of her resilience extended beyond her own career. By refusing to quit, she created opportunities for others who faced similar barriers. Her success demonstrated that discrimination, though damaging, was not an absolute barrier to achievement. This example inspired future generations to pursue science despite exclusion and bias. Her story also reveals an important truth about progress. Scientific advancement is not only driven by ideas, but by the courage to persist when systems resist change. Marie Curie's refusal to stop working despite discrimination ensured that transformative discoveries were not lost to prejudice. In this sense, her perseverance benefited humanity as much as her research itself. The phrase "never stopped" captures the essence of her character. She did not wait for permission to contribute. She did not pause her work until conditions were fair. She moved forward regardless, trusting that truth would eventually outweigh bias. This unwavering commitment allowed her to build a legacy that discrimination could not erase. Ultimately, facing discrimination but never stopping was not just a personal victory. It was a triumph for science. Her persistence ensured that knowledge advanced despite social barriers. Her life stands as a reminder that while discrimination can delay recognition, it cannot permanently suppress truth. Through endurance, focus, and belief in her work, Marie Curie transformed exclusion into one of the most powerful stories of resilience in scientific history. Science driven by curiosity, not rewards, captures the deepest principle behind Marie Curie's work and explains why her discoveries were so powerful and enduring. At a time when recognition, titles, and financial gain were increasingly linked to scientific success, she remained guided by a far older and purer motivation, the desire to understand how nature works. Her life shows that curiosity, when pursued with discipline and honesty, can achieve far more than ambition aimed at personal reward. From the beginning of her scientific journey, Marie Curie was motivated by questions rather than outcomes. She was not searching for fame, prizes, or status. She was searching for explanations. When she encountered the mysterious radiation emitted by uranium, she did not view it as a stepping stone to recognition. Instead, she treated it as a puzzle that demanded attention. What mattered to her was not who would receive credit, but what the phenomenon revealed about matter itself. This focus on understanding rather than achievement shaped every decision she made. Curiosity allowed her to persist where others stopped. Many scientists observed radiation, but moved on when the results did not fit existing theories. Marie Curie stayed with the problem because it intrigued her. She measured, compared, and tested relentlessly, driven by the belief that nature was revealing something new. This willingness to follow evidence wherever it led, even when the path was unclear or difficult, is a hallmark of curiosity-driven science. Her approach also freed her from the pressure to produce immediate results. She worked patiently for years under harsh conditions, processing minerals by hand and repeating experiments countless times. Such effort would have seemed unreasonable if motivated by reward alone. There were no guarantees of success, recognition, or practical benefit. Yet curiosity sustained her through long periods of uncertainty, allowing her to remain focused even when progress was slow. One of the clearest expressions of her values was her refusal to patent her discoveries. The substances and methods she developed had enormous commercial potential. By choosing not to profit from them, she demonstrated that her priority was knowledge, not ownership. She believed that scientific discoveries should belong to humanity, not to individuals or institutions. This decision reflected a deep commitment to the idea that curiosity-driven science serves a greater purpose than personal gain. Her lack of concern for rewards also shaped how she responded to recognition. When honors came, she accepted them quietly and returned to her work. She did not allow awards to define her identity or alter her priorities. Even after receiving global recognition, she continued to live simply and work intensively, focused on research and teaching. Curiosity remained her guiding force, unchanged by success. This mindset also influenced the quality of her science. Because she was not driven by competition or prestige, she was free to report results honestly and acknowledge uncertainty. She did not exaggerate conclusions or rush publication. Her work was careful, precise, and transparent, qualities that strengthened its credibility and long-term impact. Curiosity encouraged integrity, ensuring that her discoveries rested on solid evidence rather than ambition. Her example highlights an important truth about scientific progress. Many of the most transformative discoveries arise not from targeted efforts to achieve fame or profit, but from open-ended exploration. Curiosity leads scientists into unknown territory, where unexpected insights often emerge. Marie Curie's work exemplifies this process. She did not set out to revolutionize science. She followed a question deeply enough that revolution became inevitable. Curiosity also gave her resilience. When experiments failed or results were confusing, she did not interpret these moments as setbacks to her career. Instead, she saw them as part of the learning process. This attitude allowed her to persist without discouragement. Rewards can motivate action, but curiosity sustains effort, especially when success is uncertain or distant. Her influence extended beyond her own work by shaping how science was practiced and valued. She demonstrated that curiosity-driven research could lead to practical benefits without being guided by them. Medical applications, technological advances, and new fields of study emerged from her discoveries, even though they were not her original goal. This outcome reinforced the importance of supporting basic research, motivated by questions rather than immediate utility. The contrast between curiosity and reward-driven science also reveals something about creativity. Curiosity encourages openness, risk-taking, and imagination. It allows scientists to explore unconventional ideas without fear of failure. Marie Curie's willingness to challenge established beliefs about matter came from this freedom. She was not constrained by expectations of success or approval, which allowed her to think beyond existing frameworks. Her life also serves as a lesson in scientific humility. Curiosity recognizes that knowledge is incomplete and that nature always holds more to discover. This humility prevented her from becoming complacent, even after major breakthroughs. Each answer led to new questions, sustaining a lifelong commitment to exploration. Rewards might have marked an endpoint. Curiosity ensured continuity. In a broader sense, her story reminds us why science exists at all. At its core, science is a human effort to understand the world. When driven primarily by rewards, it risks becoming narrow and instrumental. When driven by curiosity, it expands knowledge in ways that benefit society in unexpected and lasting ways. Marie Curie embodied this ideal fully. Ultimately, science driven by curiosity, not rewards, explains both the depth and durability of her legacy. Her discoveries were not isolated achievements aimed at recognition. They were the natural outcome of sustained inquiry guided by wonder and discipline. By choosing curiosity over reward, she ensured that her work would outlast honors and continue to shape human understanding. Her life stands as a powerful reminder that the greatest advances often come from those who ask questions simply because they need to know the answers. Curiosity does not seek applause, yet it leaves the deepest mark. Through her unwavering commitment to understanding, Marie Curie showed that when science is guided by curiosity alone, its rewards extend far beyond the individual, enriching humanity itself. A legacy that still shapes modern science is the truest measure of Marie Curie's importance, because it reflects not only what she discovered, but how deeply her work continues to influence the way science is understood, practiced, and applied today. More than a century after her most important discoveries, the principles she uncovered remain woven into the foundation of modern research, technology, and medicine. Her legacy is not confined to history books. It lives actively in laboratories, hospitals, and scientific theories around the world. One of the most enduring aspects of her legacy is the central role of the atom in modern science. Before her work, atoms were largely theoretical constructs, treated as stable and indivisible units of matter. By revealing that atoms could emit energy and transform over time, she opened the door to atomic and nuclear science. Today, entire fields such as nuclear physics, particle physics, and quantum mechanics build upon this understanding. The study of matter at its most fundamental level traces directly back to the questions her discoveries made unavoidable. Her influence is especially visible in modern medicine. Techniques that rely on radiation for diagnosis and treatment are now standard practice. Imaging technologies and cancer therapies are based on principles of radioactive decay and energy emission that she helped uncover. These applications demonstrate how curiosity-driven research can lead to life-saving innovations, even when practical outcomes were not the original goal. The medical impact of her work continues to save lives every day, making her legacy deeply human as well as scientific. Her legacy also shapes how scientific research is conducted. The interdisciplinary approach she pioneered, combining physics and chemistry to solve complex problems, is now a defining feature of modern science. Many of today's breakthroughs occur at the boundaries between disciplines, where insights from different fields converge. This way of working reflects the methods she used long before interdisciplinary research became a standard practice. By demonstrating that nature does not conform to academic divisions, she reshaped the structure of scientific inquiry. Another lasting influence lies in scientific ethics and values. Marie Curie believed that knowledge should serve humanity rather than individual profit. Her refusal to patent her discoveries set a powerful example of openness and responsibility. In an era when science is increasingly tied to commercial interests, her stance remains a reference point in discussions about access, fairness, and the social responsibility of scientists. Her life reminds the scientific community that progress carries ethical obligations. Education is another area where her legacy remains strong. Modern science education emphasizes experimentation, evidence-based reasoning, and curiosity about the unknown. These values align closely with her approach to research. Students learn not only the facts she discovered, but the mindset she embodied. Her story continues to inspire young scientists, especially those from underrepresented backgrounds, by showing that perseverance and curiosity can overcome systemic barriers. Her legacy is also visible in the way science addresses uncertainty. Radioactivity introduced the idea that natural processes could be probabilistic rather than predictable. This insight influenced the development of modern physics, where uncertainty and probability play central roles. The acceptance of these concepts reshaped scientific thinking, allowing for more accurate descriptions of natural phenomena. This philosophical shift remains fundamental to how science interprets reality today. Beyond technical contributions, her legacy shapes the culture of science. She demonstrated that scientific authority comes from evidence, not status or background. By succeeding without privilege and despite discrimination, she helped broaden the image of who can be a scientist. This cultural impact continues to influence efforts toward inclusion and diversity in scientific fields. Her life stands as proof that talent and dedication are not limited by gender or origin. Her influence also extends to how society views science. Her discoveries captured public imagination and highlighted the power of scientific inquiry to reveal hidden aspects of the world. This fascination with the unseen forces of nature contributed to a broader appreciation of science as a driver of progress. Even today, the atomic world remains a symbol of both mystery and possibility, rooted in the discoveries she helped bring to light. The longevity of her legacy is further demonstrated by the continued relevance of her research. Modern studies of energy, matter, and fundamental forces all rely on concepts that emerged from her work. Advances in technology, from energy production to materials science, depend on an understanding of atomic behavior that her discoveries helped establish. This continuity shows that her contributions were not temporary solutions, but foundational insights. Her legacy also includes the institutions and traditions she helped establish. Research centers, scientific practices, and educational frameworks influenced by her work continue to operate and evolve. These structures ensure that her influence is not static but dynamic, adapting to new discoveries while retaining the principles she championed. Perhaps most importantly, her legacy shapes the spirit of modern science. Curiosity, perseverance, and integrity remain central values in research, and her life provides a powerful example of these ideals in action. She showed that science advances through patience and courage, not shortcuts or self-interest. This lesson remains as relevant today as it was in her lifetime. In the end, a legacy that still shapes modern science is one that transcends time. Marie Curie's work did not simply add knowledge. It changed how knowledge is pursued and applied. Her discoveries continue to influence theory, practice, and ethics across scientific disciplines. Through the enduring impact of her ideas and values, she remains a living presence in modern science, guiding inquiry and inspiring discovery long after her time.